Hi, this is Sung, and I'm your online maths mentor, and in this particular topic of parametric equations, it's an extension 1 topic, and what we've been doing is looking at how parametric equations work, what they are and how they work. We also looked at how it's kind of related to the parabola, okay? And in this particular episode, what I want to do is basically show you that it can be useful, parametric equations can be useful to help us to work with parabolas, and in particular, help us to find the tangent of a parabola and the normal to a parabola, okay? And we'll look at the formula for them, okay? But here's what I want to note, okay? I want to note, first of all, by starting off by saying a parametric equation, especially for a parabola, takes on the form x equals to 2at and y equals to at squared, okay, for the parameter t, right? So any point t that might be moving on a standard parabola will take on the form 2at at squared, right? But you can also have other points that move along the same parabola. Let's say the point P and the coordinates of that point P on that parabola will have parametric equations of 2ap, ap squared. So that will be the coordinates of that, okay? Now, from that information, we can actually draw or sketch, we're not drawing, we're sketching a standard parabola, plot a point T, which is your point or your locus, and that'll have parametric equations of 2at, at squared, and we can actually work out the tangent at that point and the normal of that point. So the normal would be this one here, the tangent would be this one here, right? And the way that we can do that is by basically, like, all we need to recognize is that a tangent is just a straight line and a normal is just a straight line, okay? So basically we're going to use the equation of a straight line to work it out, and in particular we've got a point and we can work out the gradient, and that'll give us the equation of the tangent and the normal using the point gradient form. Now, if you recall, the point gradient form is basically this: y minus y1 equals to m x minus x1. So do you remember that? That's basically the equation of a straight line. Now, x1 and y1 are going to be the 2at and the at squared, because that's the point of contact that the tangent and the normal make. And your m will be the gradient of the tangent. So if you're looking for the gradient of the tangent, it will be your first derivative at that point, right? Your first derivative. So how do you find the derivative, or how do you find the derivative of a parametric equation? Very good question. We're going to use this property, dy dx, which is your first derivative. Dy dx is equal to dy dt divided by dx dt, all right? Which is basically your chain rule, okay? Your chain rule from 2-unit maths basically says this: dy dx is equal to dy dt times dt dx, right? The two dt's can cancel with each other and you're left with dy dx, and that basically is the chain rule. Okay, so we're going to use that property here, right? Now let me show you how this works. All right, so we've got that x is equal to 2at. So, right, if x is equal to 2at and y is equal to at squared, dx dt, which is your first derivative of x with respect to t, is going to be 2a. Can you see that? All right, because basically your t is going to disappear. Now, dy dt, or your first derivative of y with respect to t, is going to be 2at. Do you see that? Okay, so do you see that dy dt is going to be 2at, dx dt is going to be 2a, right? To work out dy dx, you basically take this and divide by that, right? Because basically we're substituting into there, all right? So basically, well, I'm using the word basically a lot, but basically 2at divided by 2a all right, will give you the gradient of the tangent. 2at over 2a. The 2a's can cancel, you're left with t, okay? What I want you to notice is that for the tangent, your gradient or your first derivative is going to be t, okay? Let me write that down. So dy dx will be equal to t, okay? Now, how does that then help us to work out the tangent to a parabola? Well, quite simply, the tangent to a parabola, to work that out, tangent to a parabola will basically be given by y minus y1 is equal to m outside of x minus x1. Does that make sense? Yeah. Now, your x1 will be equal to 2at, your y1 will be equal to at squared, and your m will be equal to t, which is your dy dx, right? All right, cool. So I want you to notice that first off. Okay, we're going to substitute into the point gradient formula, and you should get y minus at squared equals to t outside of x minus 2at. Yep. Simplify that down. Y minus at squared equals to tx minus 2at squared. Add 2at squared to at squared to both sides. Y is equal to tx minus 2at squared plus at squared. Y is equal to tx minus at squared. Got it? So that is actually going to be the generic form of a tangent to a parabola. That bit there, okay? Which is basically what I've got up here. Okay, so let me put a box around it and then we'll work out the equation of a normal to a parabola. Okay, so hold on. Okay, so that's the equation of a tangent to a parabola. Now what I want to do is look at the equation of a normal to a parabola. Okay, so here's what we need to know. For a normal to a parabola, again, we're going to use the point gradient formula. So it's y minus y1 is equal to m x minus x1. But for this, what I want you to see is that x1 is equal to 2at, y1 is equal to at squared because that's the point of contact. But your m is going to be your negative reciprocal of your tangent, right? Negative reciprocal. So it's going to be minus, and your reciprocal is 1 on t, minus 1 on t is going to be your gradient. Does that make sense? Okay, so when you substitute all of that into there, and I'll put this in a little red box, okay, this is what you should get. So you got y minus at squared equals to minus 1 on t, x minus 2at. All right, let's multiply both sides by negative, let's multiply both sides by t, all right, so it's ty minus at cubed equals to minus x plus 2at. Does that make sense? Cool. We're going to bring this over to that side, that over to that side, and we're just going to simplify it out. So it's x plus ty equals to at cubed plus 2at. All right. So through a simple process of just cleaning up the equation, we get that the normal to a parabola is given by this particular equation here. Okay, that's very useful for us. So what's that? That's the normal to a parabola. And You might need to memorize it, but you might not need to memorize it. If you can derive it from scratch just by memorizing this, then that's fine, right? But if you can't memorize this and apply this, then it might be helpful for you to memorize the tangent to a parabola and the normal to a parabola as well. Let me just put boxes around it, and then yeah, it'll be a lot cleaner. Now, the final thing that I want to say, right, is this. So the equation of a tangent to the parabola is y equals to tx minus at squared, and for the normal it's that with the t's. If your parameter is not t, if your parameter was p, how would that change the equation of the tangent? If your parameter was, if your parameter was p instead, it would be y equals to px minus a p squared. Does that make sense? And sometimes you might even get situations where your parameter is not t, your parameter might be, say for example, some algebraic expression, so where t is actually equal to p on 2, for example, all right? And then what you would have to do is not only work out the tangent at the point t, but if you were to work out the tangent at the point p, where the relationship between t and p is p on 2, then what would you have to do? You would have to substitute p on 2 into there to work out, the tangent at p, okay, for some other point. Okay, so yeah, you will come across questions, and in the next episode I want to go through a couple of questions where we get to kind of apply this stuff and see it in action. All right, but thank you very much for watching. I look forward to seeing you on the next episode. Bye.